Antimatter can generally be divided into two types of particles, one consisting of matter and the other. Material particles are typically made up of electrons, protons, and neutrons, while antimatter particles are made up of positive electrons, negative electrons, and positive neutrons. Antimatter particles cannot exist theoretically in the standard model of physics, but they are possible in some other theories. For example, some theories suggest that if there are no constraints, positive and negative electrons may collide and be generated. However, antimatter particles have not yet been experimentally identified, and all particles observed to date have been observed as matter particles. Therefore, the existence of antimatter is still a matter of uncertainty, and further experiments and studies are needed. The Higgs particle was first discovered in CERN's Large Particle Accelerator (LHC) experiment in 2012 as one of the bosons of elemental particles that play an important role in optical astrophysics and particle physics, rather than fundamental particles such as the quark forming the hadron. The Higgs boson is a particle that interacts with the Higgs field, which is necessary to produce the mass of any particle, and theoretically determines the mass of all particles. Because this plays an important role in determining the mass of the universe, the discovery of Higgs particles is of great significance in the field of physics. The Higgs boson only exists for a very short time, which is very short, 10 to the power of -22 seconds. The existence of these Higgs particles complements existing physics theories, such as Einstein's theory of relativity and the principles of quantum mechanics, and plays a major role in the development of current physics theories. That's right. According to the mass-energy equivalent, E equals mc squared, mass and energy can be converted to each other. That is, the mass can be changed to some energy, and vice versa. But this transformation requires a lot of energy. For example, if a gram of material is converted into energy, the energy is approximately 9 times 10 to the 16 square meters per square second, 9 times 10 to the 16 joules. That's a huge amount of energy that takes more than 10 years for a typical household electricity use. Conversely, in order for energy to turn into matter, particles must collide and join together at very high energy levels. At this point, mass is produced, and energy is transformed into matter. This process can be observed in high-energy physics experiments such as large particle accelerators. That's right. The formation of matter in the early universe requires very high energy. According to the Big Bang theory, the universe had a very high temperature and density in the beginning after its birth. In this state, the particles collided with each other to form more complex particles, and then joined the elementary particles. In this process, energy and mass are converted to each other, and very high energy is required at the high temperature and density of the early universe. As proof of this, the ratio of helium to hydrogen among the elements discovered in space is consistent with the prediction according to the Big Bang theory. Therefore, it can be said that the formation of matter in the early universe consisted of a high-energy process beyond imagination.